So thank you very much for this great presentation. Now, we are going through our valuable scientist session. So I want to introduce one of the greatest scientists from Turkey, Mr. Ergin Atalar. I want to talk about him before he's been online. So he's a really important person for our country. Mr. Ergin Atalar, dear professor, welcome our session.
Thank you.
Before start, I want to say something about that. I am one of the biggest your fan. I nearly written everything that you've written before. So Mr. Professor Ergin Atalar is won the award of the 2016 National Academy of Inventors. Also, he is the Academia Europe member. Also, he is the Science Academy Turkey member too. He's the very famous person in Turkey, actually, among the inventors and the scientists. Thank you very much for joining us, and it's an honor to have you today in here. And I hope so, and I know everyone in here, these students, really eager to learn something from you, dear professor. So I want to keep it short, and you are the host right now. You can start your presentation, and thank you very much again.
All right, thank you. I hope you see my presentation, all right?
Yeah, we can see it clearly, Professor.
All right. So I saw quite a people listening. How many people are there right now?
Right now we got 51, dear professor, and a kind of things they're watching in their PCs too, not the Zoom, on their PCs in a second streaming too.
Okay, wow, how nice. Okay, so I will be talking about magnetic resonance imaging, MRI. This is what I do. This is my life. So before going into that, maybe I should introduce myself. Okay. Yes. Who is that?
One of our students forget to close his or her microphone.
That's fine.
I'm just caring of it. Don't worry about it, Professor.
Okay. All right. No problem. So this is a little about myself. I am a graduate of Bilkent University, Ankara, Turkey. Actually, I'm in the electrical engineering department of that. After graduation in 91, I went to United States, joined to Johns Hopkins University. This university is known with its medical school, one of the top medical schools in the world. And I was postdoctoral fellow when I went there. This is a typical degree after getting your PhD degree. Maybe you don't know what PhD is actually. After high school, you enter university. Engineers get the degree called BS, Bachelor of Science, and you can get a Master of Science, and then PhD is the higher degree. That actually this is the highest degree in education. After that, you can do additional training as postdoctoral fellow. This is what I did. And then I stayed at Johns Hopkins for quite a bit, like 14 years. I became a full professor there. I was appointed with the Department of Radiology. It's interesting. Electrical engineer in radiology, but this is usually doing research. And of course, radiology department is looking at the images of people and trying to find disease related patients. But there are lots of research going on that topic. I was doing research on that topic while at Hopkins. I was also appointed to be professor in electrical and computer engineering there. Also, they have a very strong biomedical engineering department. I was appointed, I had an appointment there. And then I became director of Center for Image Guided Interventions, basically looking at the images, how we can operate on people. That's the kind of things that we try to develop. I rejoined BCANT in 2002. If you see overlap between the time I left Hopkins and the time I joined, at that 3 years, I was appointed in 2 places. I was traveling back and forth to the United States and Turkey for 3 years. And then I finally gave up my post at Johns Hopkins. I became full professor in BCANT. I formed a center similar to what I was working at Johns Hopkins, and it became National Magnetic Resonance Research Center. UMRAM is the short name for that. I have quite a few publications. These are some numbers that measures how good or how you do in your research. But one of the thing I did is received a lot of US patents. I became the fellow of a society that deals with the ISMRM, and I became a member of academic European Academy and Turkish Science Academy. Maybe interesting is that I formed 2 companies. I'm founder of 2 companies. One is ClearPoint Neuritis in the United States, and the other one is Troika, it's in Turkey. All right, by the way, I would like you to stop me anytime you like. You can ask questions.
Dear Professor, after your presentation, we will move toward the question and answer session. So would you like to kindly continue your presentation? No one stop you, please. And after that, we will move toward the question and answer session.
Okay. So you want about half an hour? How long is my talk, by the way?
Please be free. We are eager to learn here. Be free. Time is yours.
Well, no, that's not a good thing. Well, maybe. All right. I'll try to. What's the planned time total? Total time, including question and answer. It's 1 hour, I assume.
Question and answer time will be just 20 minutes after your presentation, dear Professor. It will be quite short.
Okay. So I will briefly describe UMRAM and then go into my presentation. UMRAM, we have our own building in BCANT University, funded with the government funds, established in 2009. We have 13 faculty members, about 150 researchers. We have 2 researchers on MR scanners. These are expensive machines, typically used in clinical work. I'm not sure. Did anyone get MR scanned? You're young, probably you didn't. Can I ask that question to audience? Anyone? No?
No, no, we didn't.
Oh, okay. But you have seen these devices, I assume, right? Maybe I'll discuss more about these devices. This is basically devices that looks at what is inside your body. We have currently a research agreement with Siemens. This is one of the providers of the MR scanner. We have access to its software and hardware of the scanner, so we can do research on it. We have a R&D agreement with SS, and I'll discuss it a little more. We are developing SS brand MR scanner right now in the center. We have quite a large number of I guess the projects running. Maybe currently the most important one is the development of their MR system. So we already have an MR system running, but we are making it some novel features that they can have better than what is out there in the world right now. In the center, I mentioned there are faculty members. It's interesting, the faculty members are, including myself, some of them are in electrical engineering department, but psychology, neuroscience, as you can see, the radiology faculty members do exist in our team. It's a mixture. In a neuroscience program, although it looks like there are 2 faculty members, almost all faculty members are affiliated with these 2 faculty members that you see. They are solely neuroscience. The others are neuroscience jointly with the others. One of the members have both medical degree and engineering degree, MD, PhD, Meltem Karataş. So, so this is a mixture of these, some MDs, some PhDs, some engineers, some other disciplines, and we get together to do things. So in order to explain what MR does, I guess I need to tell you what magnet is. I'm sure you have seen magnets in one way or another. A typical magnet has south and north poles. When you put it in the air anywhere, it will have field called the magnetic field. It generates the magnetic field. You don't really, you cannot really feel it, but you can measure it, how much magnetic field, and this is it has a direction and strength. Also, these arrows show direction of the magnetic field lines. It just goes from north to south, basically. If you put special different ways to put the 2 magnets together, you can generate fields like uniform magnetic field around in between or you can have different kinds of fields that track. The one way to visualize the magnetic field, if you get, for example, iron particles and put it there, it seems to be aligning with the magnetic field, and this is how you can visualize, and you can get iron powder. I'm not sure you have seen it, with small pieces of iron put in a space, and if you put the magnet on it, you will see you will start to see the field lines, magnetic field lines. Of course, iron has a special place in this. Iron gets usually magnetized. Maybe what is magnetization, right? This is well, magnetization. Well, electrical engineers knows this formula very well. H represents the magnetic field. M is the magnetization. And this weird symbol over there represents the susceptibility or this is a relationship between magnetic field and magnetization. Looks like a linear relationship, but it's not always linear in any case. So one number tells you how much you get magnetized. If under the magnetic field, if something gets magnetized, it gets attracted by the field, and the ferromagnetic materials they have very strong magnetization. And so, which material do you think gets the highest magnetization under magnetic field? Which one gets magnetized? Can you tell?
Could it
Yes?
be iron?
Iron, that's right. Iron, actually there are three of them, most common ones: iron, cobalt, nickel, and they get magnetized. They are called ferromagnetic material, right? Ferro, actually, the name ferro comes from iron, actually. And this is Latin of iron. But this is not the only magnetization type. They're called paramagnetic materials. Some materials also get magnetized, but they are weakly magnetized. Tungsten is, tungsten is used in light bulbs quite often. And it is one of the strongest paramagnetic material. But compared to iron, cobalt, and nickel, it's just quite a big difference. If you put a magnet next to the tungsten, it pulls a little, but you cannot really feel it. You can measure it if you have a very sensitive instrument. But if you hold the tungsten piece and get close to the magnet, you don't feel any force in your hand. It's very weak. Lithium is another one. Sodium is another. Basically, salt also gets magnetized. There are diamagnetic materials. These are interesting. When you put the magnetic field on them, they want to escape from it. So they want to go away from it until they they repel the material. So, for example, if you put copper in your hand and you get close to the magnetic field, try to feel it. Well, maybe you cannot really, because it's very weak force on it. But you can't measure it again. Very, very weak. And there's another surprising thing is water. If you put if you take a cup of water and try to approach with the iron magnet, it pushes the water away. But so weak, you cannot really feel in your life. Did you know that we are mostly water, right? Maybe 60–70% of our body is water. Therefore, when we are in magnetic field, we get magnetized, but the magnetization that we are getting is the reverse direction as the field. Therefore, it pushes us away from the magnetic field. But this is very weak. So this is an experiment done. And if you put a diamagnetic material on top of a very strong magnetic field, it levitates. It makes it just goes up a little. Doesn't want to touch, right? And in fact, there's a famous experiment. They put a frog inside the magnetic field. Frog is just going up. It's not touching, right? It's just the surface is just get the frog levitated. In theory, if you put the magnetic field on the floor and you can walk on it without touching it, but touching the floor. So it levitates you, it puts you a little higher. That's very interesting. But this in order to have this effect feasible, you need to have very, 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 very high magnetic field. We typically don't have that much field. Therefore, we don't feel any magnetic field. Right? Earth has a magnetic field. It's about 25 to 60 microtesla. Tesla is the unit of the magnetic field. Tesla is the very famous person, a scientist's name, and it becomes the unit, name of the unit also. It's a big magnetic field. If you get, when we say magnet, we usually mean a permanent magnet. There are many types of permanent magnet. This magnet is one of the strongest permanent magnets, and 1.3 Tesla specifically on this field strength. There are also electromagnets. Electromagnets is this: when you apply current to a wire wound like this one, it produces a magnetic field. In fact, this is interesting. This way of generating magnetic field is the most popular one, rather than using the permanent magnets. And you do anything in the field of electromagnetics, and you generate the field by applying current to a wire basically, which is wound around, typically around the iron to enhance the magnetic field. No, modern, yes, any question? Yes. No question. Okay.
Actually, there is two questions,
Okay.
dear professor. So, may I ask you there is two questions for you.
Okay.
The one of questions coming from the Michael, who's from Italy. Are there any artificial ferromagnetic materials in the world?
Wow, that's a very clever question. I don't know the answer. Probably there are, but I don't know. I don't know.
Okay, so move to the second question then.
Sure.
Does that mean hydrogen and oxygen are diamagnetic, or is the bond they form or reaction between them diamagnetic?
Wow, such a powerful questions, right? Well, the oxygen is diamagnetic actually, and when they form together, actually, this is we measure together, right? As together, also diamagnetic. Excellent.
Excellent. So it is there's only two questions because they keep their questions to question and answer session.
All
you
right.
May continue if you want.
All right. Excellent. Wow. I was not expecting such high quality questions from
students. Right?
Students. Wow. Mind blowing. MR scanners are typical magnetic fields are 0.5 Tesla, 1.5 Tesla, 3 Tesla, but basically pretty strong magnetic fields over there. It's possible to use even Earth's magnetic field to image, but we usually use these fields, and there are actually studies going on, 7 Tesla and 10.5 Tesla as well. The magnet that you are saying, of course, the person goes inside the magnet and they lie on it. They lie in it, and the magnetic field, typically head to toe direction, right? And this is yes.
No, dear professor, you may continue your presentation. It's as I said, some students left their microphones on.
That's fine. That's fine. Okay, so there are many types of MR scanners. The one that you have seen in the left is the one similar to what I have shown earlier. It's they call it horizontal Bohr magnet. If you put it in vertical, of course, the field you can people cannot really jump inside that, right? But they put sometimes the horizontal and put material inside to image rather than person. But there are other magnet types, they call it open magnet type. This is not really totally open. Sides are open and field is vertical in this direction. And patient typically lies inside the magnet. So when you get these images with this device, you see basically water distribution inside your body. This is the brain images, you see the cross-sectional view of brain of a person. It's very interesting. The thing that we are measuring is the magnetization of the body, in this case, brain. So magnetization, as I said, is very small, very, very small. It's with the force, you cannot really detect very much unless you have extremely high magnetic field. Here, in this field strength, the person cannot feel anything, but we can measure its magnetization with the phenomena called magnetic resonance or nuclear magnetic resonance. The magnetization start to rotate or start to generate signal that you can detect if we apply an electromagnetic field to the body. And this is basically the source. What you are seeing is basically magnetization distribution inside your someone's head, right? There are many techniques to modulate this magnetization, and this also changes the contrast of the image. Therefore, we can start to see, understand what materials or what tissue structures are there in the brain. This topic has been under investigation since 1980s, 40 years now. Every day we get a new way of looking at the body. This is what you're seeing is two different ways of looking at the head in different slices. Okay. What is the future of magnetization in transport vehicles? Oh, wow.
Dear Professor, if you allow us, we can we can use that questions in the question and answer session.
Okay.
It will be more useful and you will get much more time to answer.
Okay. Okay. All right. All right. All right. I'll take it later then. Brain. Brain. You see, this previous images that I saw, I showed you, was also brain, but this is another view. The previous images, I call it axial view, where I'm not sure you see me. That's the axial view, and this is we call the sagittal view. This is more easy to understand. You see the brain very well. You see the person's nose, mouth, tongue, all the other components, and very, very nice to observe these details. Of course, for us is the curiosity, but medical doctors looks at these images to understand what's wrong with the brain. I'm not sure this will play, but no, it's not playing. But we can get the whole brain images. You don't need to look at only one slice. You can look at every part of the body. Another property of this is you can see the blood vessels, right? Here is the blood vessels of the brain are visible with MR, right? You can, this is knee, what a beautiful knee image, right? I'm not sure you follow the soccer games all the time. If one of the players get injured, they put the person into MRI because then most likely they injure their knee, or their knee is the most important one to look at probably. And MR is the only imaging technique that gives that much beautiful pictures. So, of course, I will not be able to explain all these details, what we are saying, but typically what we are saying is water, and if bone itself does not have much water in it, therefore it appears dark. You see a dark structure around the joints. These dark structures are the bones. But the bright one is what is inside the bone, and of course what is outside the bone. One can visualize what where the fat, where the muscle are from these images, and look at other structures like a cartilage and skin and other parts. This is another beautiful image. This is the image of our biggest blood vessel called aorta, connecting to kidneys. And you see the vessels connecting to kidneys are called renal arteries. They're all visible under MR. If there is, of course, something wrong with the kidney of the person, you can visualize with the MR very nicely. Well, what is inside the MR? MR is a very complicated device. In fact, I mentioned earlier only the magnet part, but in our center, for example, we mostly work on the all other parts rather than magnet. We call the gradient system that has that's used for encoding the images, to acquire the images. We have very strong RF amplifiers, and we send radio frequency pulses to the body and received radio frequency pulses, received signal, and then convert it in a way that computers can understand, and programs are written on the computers to reconstruct the images, right? So all these components are pretty difficult to make, and they're working on it. The magnet itself is also tricky to work on. They are typically superconductor magnets. So I mentioned that you need to apply current to generate a magnetic field, but when you apply current to a wire, the wire gets hot. The reason that they have a finite resistance. But if you use superconductor, basically they don't cause any heating. So you can basically, theoretically, you can apply very high current, still don't get any heating. Therefore, you can generate a very high magnetic field. But in order to put this wires into that state, you need to supercool everything. These are cooled below minus 270 degrees. Very, very cold. Absolute, it's very close to absolute zero, basically. Absolute zero. The biggest problem, of course, that you need to keep the temperatures low all the time. So it is basically put into a vacuum so that it won't radiate heat towards inside, right? So that they don't heat up. They put liquid helium to cool this, typically. There are permanent magnets, but they are lower in field. And once the magnet is running, there's a process called shimming. Is another thing. We want the magnetic field not only very high, but also very uniform. The variation within the body should not be more than 1 part in a million. When you put this magnet together, of course, when someone puts the magnet, of course, they want to generate a uniform magnetic field as much as possible, but then it won't be uniform. I'm not sure I have seen tires being shimmed, right? When you cars typically tires vibrate if you don't shim. So once in a while you need to take to a mechanic who puts in a machine, basically rotates the tire very rapidly and sees the rotation and puts some mass in some parts of the tire to make it not the right vibrate. This process is called shimming, and it is similar here. We put some magnetic materials around inside the superconductor magnet in order to make the field uniform. This is a very important part of the process. But once get this device is running, you can get beautiful images like this. The other thing we need to do is we need to send RF pulse to the body and receive this body. These are very similar frequencies as we used in communication. TV channels run in broadcasting in this frequency range. So we get very weak signal in MR. Put basically antenna is under the body to get this weak signal. But we put everything into called the Faraday shield. That means we don't want to get the broadcasters into our receiver. So the field, the electromagnetic field inside the room has to be zero or very close to zero before we start to get the image. We need to get on the signal from the body since this is very big. So the whole room is insulated with the copper, and when you walk into the MR scanner, you're working in a basically copper. All the walls are copper, so you're inside the Faraday cage. So I'm not going to talk much about history, but this has been around for a while. Almost 100 years ago, we know this NMR phenomena, but last 40 years, we're working on the images. I mentioned there are many ways of imaging. This is, for example, one way of imaging. You see, if you see this type of images, it's just beautiful, because now in the left two images, blood vessels are not visible. In the right top image, you see the very bright signals. They are coming from blood vessels of the brain. This is the same brain image with different parameters of MR. You can get quite a different contrast, and these are used to get the images. One other very, very interesting property of the MR is you can get diffusion images. What is diffusion? If you, I'm not sure you know what diffusion is. If you put ink inside a cup of water, it diffuses the ink. It diffuses inside the cup of water. And if you don't put anything, of course, if you happen to sit on, well, it is not possible, but if you can sit on a water molecule, any molecule, you will end up with finding yourself in other places, because the water diffuses inside the water. This is we call the self-diffusion. This is what we measure, self-diffusion over there. Of course, if there are pipes, structure that you want the image is pipe, it diffuses along the pipe. In the brain, we have all these interconnections between the different parts of the body. It's a basically electrical circuit. Therefore, with this technique, you know which part of the brain is connected to what part of the brain, right? This is connection imaging, basically. This is, you can get the 3D view of the connection. You see this beautiful diffusion images, but you can get the blood flow imaging as well. How much blood is flowing in the brain, you can look at. This is blood flow, but this is blood may flow in your blood vessels, but it won't, if it doesn't go to the tissue, that's a problem, of course. But we can measure how much blood is in the tissue. This is, we call it perfusion, right? So maybe we can image heart. We can image most of body parts. This is another thing that we're working on. This is called functional imaging, fMRI. We let the person, for example, tap the finger. So it just does this inside the MR scan. And we say, stop tapping. And then we tap it again, stop tapping. Of course, when you try to do this finger tapping operation, part of your brain works. And we can tell which part of the brain is related with your finger tapping, right? Of course, finger tapping may not be a very critical thing, but you can give other tests to the person, and the task-related parts gets enhanced in the brain, and you can visualize that. This is very important for neuroscience. They want to understand how brain works. This is one of the greatest tools in learning how brain works. This is one example. One part of the brain is working for a given stimulus. We can do operations under MR. Well, we're recently working together. You see the last three authors. Kamil Urbev is the head in the University of Minnesota. Myself and Yiğitcan Ergin is one of my former students who is in University of Minnesota. First student over there is Iranian, but he is a graduate of Bilkent University. He is my student as well. In any case, we're working on the imaging at 10.5 Tesla scanner. This is one of the things that we're working on. Okay, so I will stop here, and maybe I'll try to answer your questions at this point.
So, firstly, it was really great presentation, and we learned a lot of things. Thank you very much, dear professor.
Sure.
Let's continue to our question session, QA session. So there is a lot of questions in there, and we will start with the first question from Clara. What is the future of the magnetization in transport vehicles?
Oh, it's not my field, so I don't know the answer. But I have seen people working on magnetic levitation. So I didn't mention here, superconductors are diamagnetic, so they repel. Actually, they're very strong diamagnetic materials. They put diamagnetic materials under the train, for example. That just levitates the train. And therefore, with very little push, you can move the train. But this is a very expensive technology. But people are working on that. I don't know much about it.
If you say expensive, I'm more move toward the other question. Why the MRI devices so expensive? Is it really hard, the engineering behind the prediction of these devices?
Right. And engineering is the most difficult part. The magnet itself is expensive, but it's about maybe a third of the cost of the system. There are other things that they're working on is 2/3 of the scanner. The RF amp, when I start working with the Aselsan people, they said we can do everything because we do radar, for example. We send they said they sent very strong electromagnetic fields to see if there's a plane passing by, for example. And they measure the reflection of the electromagnetic fields coming from the plane. They have to apply very strong electromagnetic field to detect that. But the field that we are applying is more bigger than the field that they apply. So there's very challenging hardware, basically. But this makes the system cost higher. Engineering is one of the biggest cost, of course.
So in the future, it will be better or going worse because the technology is going high, but some of the courses is going down. What is the lying behind of this technology in the future? What they expect?
Of course, it's difficult to predict what the future will be. But when what I see here is some people are trying to make the system cheaper, produce similar image quality with a cheaper system. There's a big trend these days about that. The second trend is forget the cheaper, I want to get better quality images, then of course, then they make the system more expensive, right? So, I mean, there are benefits going in both directions. One is, of course, more widespread use of the system makes it less expensive, cheaper. Of course, everyone likes good quality images with less money. But the second thing is there are things that you cannot see right now that you may be able to see with if you have a better system, right? We need both of them.
Yeah, all right. So Mrs. Partbayan asked, why the people who has metal implants like pacemaker can't take MRI? Does that have to do with the magnetic field? Is it true, the professor? Because there's a rumor who is surrounding in the people, you can't go MRI while if you have got any part of metal or have you got a tattoo. Is it true or false? I don't know.
It is mostly true. Or what I should say that we need to examine, or the radiologist or the technologist or taking this should examine the person before going into scanner with the metal implant. The MR is very safe if you don't have metal implant, right? But if you have a metal inside to you, you have a problem. Well, I have an analogy, but maybe you will not like it very much. You know, the microwave oven. While we are in the MR scanner, we are in the microwave oven, in a sense, because they apply a high RF radio frequency field to the body. Of course, while in the microwave oven, the power of the microwave oven is adjusted so that it doesn't boil anything, right? That's so it just otherwise then aim will be cooking. This is not our aim, of course. We don't want to cook, but anyone, if anyone tried, if you put a fork inside the microwave oven, it just becomes like sparks come out.
Sparks explode. Yeah.
Right? Therefore, the metals basically concentrates all the magnetic field, electromagnetic field in certain locations, and they heat up at that location. This is in regular. We assume that body heat that we are applying to the body is uniformly distributed in the body, but everything concentrates on one location. That's better. You may burn that place. I have seen people with the tattoo get burned inside the MR scanner, not very often, but if they are not very careful and people don't show this is important. Actually, I may have a slide showing on the safety of this. Maybe I'll go. I'm not sure. So this is the person goes inside the MR scanner with the neuro implant, and brain got injured. Right. This person did not die, but close to dying, seriously injured. But this is only documented case like this. People are afraid to repeat this one, of course. Therefore, we are extra careful not to do similar things again.
Okay, that's quite impressive. So there is a last question. Actually, before the last question, can enzymes or liquids in the brain can be shown or a chemical transformation or reaction by effector MRI?
Yes. Well, this is again a very excellent question. Yes, that's possible. In fact, NMR is one of the biggest tools of the chemist to figure out reactions. They put, of course, different materials together and examine with MR. They know the new molecular structure. During imaging, of course, we have this capability as well. We can look at the different components, how they connected to each other. But unfortunately, to do this, it takes a very long acquisition time. And patient cannot stay very long in the MR scanner and they get tired. But if they can stay, they could stay for days. We could learn much more things about the patient. But of course, this time you spend to acquire data is the limiting factor rather than the things that we can do with the MR.
So, dear professor, right now, a lot of high school and university students are watching you from Ireland to Nepal. So we are in the streaming on Europe to Asia. So what do you want to say to them if they want to be being like you, to being a successful inventor, successful scientist in their life? So have you got any suggestions? Maybe to us too, of course.
Very simple answer is very simple, but hard to do. You need to work hard. That's it.
Okay. You heard the professor, guys. You have to work hard. It's very simple.
So just there is no other way. You need to work hard. You need to work hard. You need to work hard. That's all.
Actually, this is the quite simple, hard to do, and wisest quote that I heard a lot of time. It was quite beautiful. Thank you very much, Mr. Atalar, dear professor. Thank you very much to have you today, and we learned a lot of things.
You're welcome.
And thank you. Thank you very much, teacher.
Thank you. Bye-bye.
See you later.